fly. Even this thing flies. After a fashion, anyway. The question is, what's the biggest thing that could possibly fly? Over the last few weeks, thousands of you have written into the website with scientific questions and suggestions for experiments that we can do to answer them. This week the question is, what's the biggest thing that could fly? So I brought the shack to Cardington in Bedfordshire, to this amazing hangar, which was constructed in order to build the R101 airship, the biggest aircraft ever built in Britain. What I hope is that these amazing surroundings will inspire the Science Shack team to build me a giant aircraft that won't suffer the fate of the R101, which crashed into a hillside in northern France in 1930. Now, there are only two rules. First of all, their aircraft has to be big enough to carry a person, me. Second, it has to be made out of paper. The team wanted a real paper expert and called in Glenn Davidson. He's not an engineer, but an artist who specialises in making huge structures out of paper. The choice seemed to be heavier than air, a plane, or lighter than air. Well, the biggest things to have flown so far are airships and balloons. So I've asked Glenn and the team to try and make a man-carrying hot air balloon entirely from paper. Glenn, I've no idea what you're doing here. It's very complicated. You've laid out about an acre of paper.
Yes.
Is that what you're going to make the balloon of?
Not the stuff on the floor, but the great roll that we've got here, which is about 2.3 metres wide.
This stuff?
This stuff,
okay.
yeah.
Now, is it strong?
This stuff is fantastic. It's 46
it's
GSM.
Not... Yeah, that's half the weight I use in my printer.
Exactly.
It tears easily.
It does.
It's going to take my weight.
I think it may, actually.
The balloon is going to be made from 600 square metres of paper, and just marking and cutting it out is going to take hours, so I let the team get on with it. Nowadays, the sheds at Cardington are again home to a high-tech airship factory. Some of these machines are meant to hover above cities, replacing communications satellites. I wanted to know more about the history of this amazing building, and Alex Travell, who runs it now, knows all the details. So tell me when this building was built.
1917, for the First World War. During the First World War, there was a great problem with blockading the Germans in the North Sea.
Right.
And they did a lot of that work, a lot of the link-up pieces between the ships with airships.
Right.
So what they did was they did a meteorological survey of the country and said the best place to do that is in Bedford. So they built a hangar here.
So how long is this building?
It's 813 feet inner dimension.
Right.
It's 180 feet and 4 inches side to side, and 157 feet from here to the centre catwalk.
Have you walked along there?
I have indeed.
I don't want to do that. It's hard to think of this enormous building being filled, but that's what the R101 did. When it was finished in October 1929, it was 224 metres long. But there wasn't enough lift. So over the winter, she was cut in two, and an extra 30-metre section was added in the middle. The plan was to run passenger services to Karachi and New York. And in 1930, the R101 made the first ever east-to-west crossing of the Atlantic by air. But in October of that year, she ran out of control on her way to India and crashed into a hill in France. The planned Imperial airship service never recovered and was eventually abandoned.
Pull harder. Great. Let me come over.
Don't be fooled. It may look like a pile of paper now, but Glenn has a cunning plan. So, Glenn, this is actually it, is it?
It is.
This is
It
my beautiful balloon.
Your beautiful balloon.
Not
absolutely.
quite that lovely colour, unfortunately. I'd love a pink one.
Would you?
Our balloon is going to be huge. We know that a conventional hot air balloon has to hold about 600 cubic metres of air to lift 200 kilograms, a bit more than me, which means a balloon 32 metres in circumference.
Why do you want it this shape and not just a sphere?
But it's optimised for putting as little stress on this fabric as we possibly can. So it's
Having got a shape that looks like a balloon, Glenn uses another piece of software to unwrap it, rather like opening a birthday present. We have to make a giant version of this shape and then wrap it up again to make the full-size balloon. So the previous night in the hotel, Glenn had the team translating the computed figures into a template for the gauze, the shapes that make up the balloon envelope. Fortunately, the balloon is made of 32 identical pieces, so we can cut them all at once. On the other hand, we have to be terribly precise, because any errors will be multiplied up 32 times.
Balloons and airships are really a bit like bubbles. They get lift because they are less dense than the air all around them. We're living at the bottom of a great sea of air, and anything that's a bit lighter than the air will be pushed upwards. Now, I've got here some bubble mixture, and by turning on my blue knob, I can make bubbles that are filled with oxygen, which you might think would be a good thing, but in fact oxygen is more dense than nitrogen, which is the main constituent of the air, and so oxygen bubbles actually sink. And obviously it wouldn't be much good filling a balloon with oxygen if you wanted to get lift out of it. You'd actually get drop instead of lift. However, I can turn on my red knob and I can then fill my bubbles with hydrogen. And look at the difference. Hydrogen is the lightest gas in the universe. And so there's lots of lift because these bubbles have got very, very low density. And the air is much more dense and pushes them upwards. The only problem with hydrogen is that it's flammable. And if it gets near a flame, it can be a little bit unpleasant. Like that. I wouldn't really want to be in a balloon or an airship held up by hydrogen. Now that is what happened to the Hindenburg. She was the biggest airship ever built. And in 1937, she was just coming in to land at New York and she caught fire. Not an explosion, just a fire, but it was spectacular. It was terrifying. And yet, in spite of those sheets of flame, 2/3 of the passengers survived. I don't know how they got out, but somehow they did. That fire was the end of the airship industry, which was perhaps a bit unfair, because all those passengers survived, whereas today's air crashes, they very rarely do. And what's more, today's aircraft carry enormous amounts of kerosene, which is just about as unpleasant as hydrogen.
At last, the shape of the gauze is revealed, and you can begin to see the task that lies ahead. Now we have to make 32 seams, each nearly 20 metres long. That's over 600 metres of seaming, with everything matching up precisely. I'm beginning to wonder whether we have enough time.
Now, there's a colossal amount of work to do. We've cut the thing out, but gluing it up is going to be a major problem. Fortunately, we appealed for help, and look what we've got! It's the cream of Bedford College? Yes. Aeronautical engineers?
Art Foundation course.
Art Foundation. But you know about sticky back plastic. You can handle paper, sticky tape, work as a team. Great.
You need to get the end wet. These ends, these can really understand.
Glenn insists on absolute precision. You do it if you were making an airframe, and you have to be millimetre perfect here too. But I'm worried about how complicated the job's getting. Each bit of tape is just 300 millimetres long, which means 2,000 individual operations of tearing, wetting, sticking and folding.
Now, nothing less than that will do. So anything less than that comes off.
How much should we overlap the other tape?
By 1 centimetre.
The plan is to stick the 32 pieces into 16 pairs, then join the pairs to form 4s, and so on until the envelope is complete.
The basic problem about making a hot air balloon out of paper is that paper is flat and the balloon is spherical, i.e. 3-dimensional. Now, the way they're doing it is to make a whole lot of shapes like this, long, thin lozenge shapes. Now 9 of these have already been stuck together, and here they are. This is the bottom, all glued together, and there's the top, and you'll see that the final thing, there's the inside with all those markings, the final thing will actually be roughly that shape, because we haven't made a third of it yet even, and then it'll be very much balloon shaped. Isn't that a lovely thing? And the gluing, the taping down the edges is absolutely critical, because not only do they have to fit together, but there must not be any holes for the hot air to escape. Another problem about the taping is that if they get it slightly out of line, say one of these slightly moved up from the other, then the whole thing will begin to distort, and that will put enormous amount of stress somewhere in the structure, and it might easily tear, and again, all the hot air will escape.
By the end of the first day, the students' sticking technique is getting much faster, but we've only done 9 seams, with the hardest part still to come. Amazingly, the Bedford College Brigade turn up at 8 the next morning ahead of the Science Shack team, keen to crack on. With the new day, a new plan. Making sections of 4, then 8 gauze is clearly a waste of time because so much paper has to be moved around. They're going straight to the 16 segment stage, joining all the pairs up like an accordion. In case you're wondering about fixed wing planes, there are 2 record holders. Howard Hughes built the Spruce Goose, a vast wooden flying boat with a world record wingspan of 97.5 metres. She cost millions and was pretty useless. Her maiden flight in 1947 lasted 2/3 of a mile at a height of 20 metres and was the only flight she ever made. Slightly smaller in wingspan, but much larger in every other way, is this, the Antonov 225. At 600 tons, it's the heaviest thing ever to have flown, half as heavy again as the biggest 747. Only one was built for the Soviet space program in the late 1980s. But could you, in principle, build an aircraft even bigger than the Antonov or the Spruce Goose?
We've talked to the aeronautical engineers, and they reckon there isn't really a limit. You could just extend the wings, extend the fuselage, and so on. And if you had powerful enough engines, and if you could go fast enough, you could build a plane as big as you want. But there might not be a lot of point.
A plane bigger than a jumbo jet would have to fly faster and higher and would use much more fuel.
What's more, if you built bigger planes, they wouldn't fit into airports because they need longer runways, which don't exist. They need tougher runways, which you'd have to build. And the passenger gates are designed to just accommodate a 747. And if the plane was any bigger, well, they are talking about building bigger ones. They'll have to fold their wings to fit into the gap. So it should theoretically be possible to build a bigger plane, but it might not be worth it. However, even though planes might not be any better if they're bigger, with airships and balloons, the story is totally different. Small ones simply are no good at all, and the bigger they are, the better they get.
By far the biggest balloon ever, much bigger than the Hindenburg, is planned to be built next year. It's British, and it's meant to break the balloon altitude record. It will go so high that one of the pilots, Colin Prescott, is already practicing getting into his spacesuit.
That's it. Right. Now, Colin, your plan is to go higher than anyone has ever gone before, is that right?
Yes, there's a wonderful history. No attempt has been made at an altitude record in the balloon for over 40 years. And the current record was set by 2 US Navy officers as part of the American space program in 1961.
How high did they go?
They got to 113,740 feet.
But Colin and his partner Andy Elson plan to go to 135,000 feet. Space officially starts at 100,000 feet, so this is the first British mission to space.
How big's your balloon? Would it fit in here?
No, this is about 150 foot high, this building, but which is enormous, but we'd need 8 of these. It's about 1,200 feet high at launch.
1,200 feet high?
Yes, about 7 times the height of Nelson's Column.
Gosh. And presumably it's quite small to begin with, is it?
It's small in terms of volume, yes. I mean, I can't put it any more delicately than it looks rather like a condom at launch, with a little bubble of air at the top. But that expands about 350 times on the way up.
So it becomes more or less spherical once you've got out there?
Yes, it becomes a bit like an onion, in fact.
Right, even more than spherical?
Yes.
Right. And is it made of some incredibly expensive material?
The material itself isn't expensive, but the putting of it all together is quite expensive.
I imagine
it's
that.
actually polyethylene. It's rather like the...
It's a polythene bag?
It's a polythene bag, yes.
How wonderful. Where are you going to launch from?
We either want to launch from the North Devon coast, because the stratospheric weather at the time we want to go, which is July, August, is always to the west. Or we're talking to the Royal Navy about whether we could possibly use an aircraft carrier.
And what are you going to do up there? Apart from saying, hooray, we've got here, you can't plant a flag or anything, can you?
No, but we can admire the view.
Yeah.
And we can relay those images down to Earth. And that's one of the things that really appeals to me, is just that one image of two little spacemen on an open deck under the biggest balloon in history in a totally black sky with the whole curvature of the Earth underneath. It's kind of fun, isn't it?
Your open deck, you've got no protection, no windscreen.
No, it's an open deck.
Kinetic 1 should be ready to launch on the 1st of July 2002.
They're going to send me up in a hot air balloon.
Are they?
Yes.
Is that safe?
No, I'm sure it's not safe, and I hope I'm only going about 6 inches. Have you got any advice for me?
Bend your legs
Bend my legs.
in case it all falls apart.
Right, because it's better to land with your knees bent.
Absolutely.
You might not break a leg.
Yeah.
Thank you very much. I really appreciate that advice, Sunil.
Very nice to see you.
Thanks, and
Great.
you.
Because this is a hot air balloon, we had thought of using fireproof paper, but Glenn was worried about using an untested material. Luckily, the 400-kilogram roll wasn't wasted. We needed a smooth area for the launch to avoid puncturing the envelope on the rough floor.
How much does the paper weigh?
The weight of the paper, well, it's 46 GSM.
Right.
So we've got a surface area of
350 square metres.
Yeah. So we could do that here.
All right, go on then.
350 square metres times 46
grams.
There it is, 16100. So this must be
That's only
161
kilograms.
kilograms.
That's scary. That's more than I am. So we've got to lift basically 3 times my weight almost.
Yes.
Are we going to do it?
Who knows? I really cannot imagine how the next couple of hours are going to go. That's it.
Actually, we got the decimal point in the wrong place. It weighs only 16 kilograms. But weight isn't the only concern with a paper balloon.
Fantastic.
Now, there's a big question about how much heat we need to hold up my hot air balloon. This is a small model with only 8 panels made of the same sort of paper that we're using for the big one, and we're blowing air in at the bottom with a paint stripper that's blowing in 1500 watts. Now, the temperature outside in the air is about 7.6 and inside 49.4. So we've just got over 40 degrees of temperature rise. We're measuring the temperature at the top, and it's not going up, it's now stable. And that means that we must be losing 1500 watts from the surface of the balloon. Now, unfortunately, the big one, designed to carry me, has got a far bigger surface area, and their calculations suggest we would need, how much?
90 kilowatts for this.
90 kilowatts of heat going in order to get me off the ground. I don't think that's possible. I think I need to lose weight quickly.
The progress has been going quite well. Of course, one of the things is that nobody here has built this kind of form before and used these kind of techniques to do it. There's a lot of skill. To stick a wet piece of tape, a nice long one preferably, onto 2 edges and get it absolutely millimetre precise is a skill. You need dexterity to do that. And the whole group have had to learn.
So, Glenn, is this the last seam?
The last gauze, yes, to be connected. The last seam.
You've got to join that bit there
Yeah.
to that bit there.
Yes.
So you've got to get all this lot out the way.
Yes. Okay. 10 minutes to finish.
At last, we have an envelope. The Bedford College students have done a magnificent job, changing from art students to aeronautical engineers in the space of a single day.
We've got a terrific Science Shack website, And if you go there, you can put in questions or you can suggest ways we can answer questions. It's not too late to get involved with the series. We've had an email today while we're making the programme from Alex Prail, who suggests we could make an infinitely large flying machine simply by taking an infinite number of helium party balloons and joining them together. Well, maybe. But when you think about it, there'd be real practical problems. 3 months ago, a chap did take 600 and lifted himself up 11,000 feet. But if you take an infinite number, it would take an infinite time to fill them. And even if you had thousands of people doing it, gathering them all together and getting all the strings tied up, and they'd all start leaking, I think it would be impractical, to say the least. But nevertheless, thanks for the suggestion.
Rather than attempt to join the very fine points, the plan was to cut them off and make a new circular piece to fill the hole at the top of the envelope. But it won't lie flat enough to let us draw a template. So Glenn has a brilliant idea. Why not use the bits we cut off?
Unfortunately, the whole thing has been binned. It's been thrown into the waste, and this is all that remains. So we've got to find another way of sealing this end. This is really the last job of before we can inflate.
I'm on fire extinguisher duty. Carbon dioxide, pull out the pin, point the horn, squeeze the handle. No problems.
We're getting to the point where we need someone who knows about balloons. Stuart Townley tests the burner, which will inject heat into the envelope. Suddenly, the mood changes. We've been thinking of the envelope as a shape we had to make, but now we have to think of it as a balloon. And the idea of putting that much flame into this much paper really has me worried. But how am I going to be attached? The plan is to use reinforced parcel tape and hang 16 lengths from the crown of the balloon. 8 to lift me, 8 for the team to control the envelope. Then a real blow. The flame test has worried everyone, including the airship company. If the balloon catches fire, there's a real danger of burning paper landing on their million-pound airships. We can't launch from this end of the hangar. Jonathan has to tell Glenn to move the delicate envelope to the far end of the building.
Sorry, run it where? Down there?
Yeah.
Okay, because of the wind, yeah. So if we did it in two, so you and I, arm in arm like this, and we carry it like that, like pallbearers.
I'd been really worried about moving the balloon, and clearly Glenn was too, but in fact it felt much stronger than I'd expected. Perhaps there was a chance this thing could really hold someone up.
I'm opening it up now, and we'll just feed a bit of air in and see how it unrelaxes.
Right, so at last we're inflating it. Just filling it with cold air to get the shape up so we can then start pushing in the warm air. And basically it's just a simple extractor fan pushing air into it. And gradually you can see it taking shape.
There's absolutely, completely no. Mind you, it does offer an opportunity. Let's have a look inside. Oh, fantastic!
The main issue really is to not allow the balloon to free fly off uncontrollably. So now we've got the load tapes that come down. What we'll need to do really is split the load tapes up into pairs, allocate certain people onto those load tapes. I'm going to induce then the hot air from the mouth of the balloon. The hot air goes in. What we need to expect to happen is it's going to travel up to the top of the balloon, and then the balloon will then hopefully, slowly but surely, stand to attention. That's when, Adam, you need to be very close by, because once we get the thing standing up with the aid of the big cherry picker platform, the load tapes we need to just sort out at the top of the balloon to bring them down and basically get you strapped onto it. I'll be quite close next to you with the flame to induce more and more heat to hopefully obtain lift.
We're still seriously worried about fire, so the fire brigade is on standby. If the envelope catches, Stuart reckons it will tend to rise up to the ceiling, 150 feet up. the firefighters are confident they can reach there with their big hose, which is rolled out and pressurised in case. I just hope I'm not still attached if this happens. I must admit the balloon looks stunning. Now fully inflated with cold air, it looks exactly like the computer picture we started from 2 days ago. Glenn and the team have done an outstanding job. It clearly is a balloon, and I can't wait to get on board. Load tapes are attached to the top of the envelope, but even inside the building there's quite a breeze blowing, and Glenn is worried about the inflated balloon getting out of control. So the new plan is to pull some of the tapes over the top to help control the balloon as it's heated. We want to get the envelope as upright as possible before putting the flame in, so that there's no paper immediately above the burner.
I think that's fine for the time being, thanks.
But we seem to be losing control of the envelope. Either it's slowly deflating because the fan is now switched off, or the tapes are pulling it round.
Can you stop pulling everybody? You're pulling it over. Come in. Relax.
It's difficult to be sure, but it looks as if the crown piece came away from the paper, setting up a tear that ran down the side of one of the seams. Perhaps if we got the heat into the balloon sooner and got it upright, it would have been less stressed. Maybe we could have used slightly heavier paper. But we don't know. Not everything is predictable.
It was so close. So close. Such a lot of design effort, hard work, something like 200 person-hours just for building it. 340 square metres of paper enclosing 500 cubic metres of air, something like 3/4 of a tonne of air. And it was just about inflated. These tapes were over the top. They were going to hold it down, and 8 of them were going to lift me up. I didn't really believe this would work. This is the most ambitious project the Science Shack team has taken on, and I didn't really believe it would work. I thought they'd bitten off more than they could chew. And then I began to believe it about an hour ago. It looked so fantastic, inflating here on the ground. And I was getting quite excited, and it's really sad. I guess there was just too much tension. The paper is very flimsy, and it's gone along a seam. Probably the sticky paper has a slightly different elasticity or folding or something, and there was just too much tension there, and once it had gone, the whole thing ripped very fast. And I don't expect we'll have the chance to do it again. See you next time.
If you have a science question you'd like answered, a team of experts from the Open University is standing by. All you have to do is visit the Science Shack website at www.bbc.co.uk/science/scienceshack.